some of you have seen parts of this talk before. Some of the slides will look familiar, in particular the introductory slides, but I think none of you have seen the entire talk before. So in the literature on thermodynamics, there is something called Landauer's principle. Some of you have heard of it. Some of you have not. If you have not, don't worry. I'll tell you what it is supposed to be. And as David alluded to briefly yesterday, there's been quite a bit of controversy about the status of it in the philosophical literature. And a number of years, the origin of this is a number of years ago, I was writing an article for the Oxford Research Encyclopedia of Physics on philosophical issues in thermal physics. And I read through all that literature. By the way, advice to the junior people in the audience: do not agree to write an encyclopedia article or review article pre-tenure, because it literally is reading 18 papers to write one paragraph, right? So I read through all this stuff, and it occurred to me, yeah, well, actually, there is a theorem that I think is what people have in mind when they talk about Landauer's principle, but I'd never seen a clean proof of it. So I wrote up what I thought was a nice, neat proof with all the assumptions spelled out explicitly, and I published it. It was intentionally designed not to be vulnerable to the criticisms of Landauer's principle in the literature. In particular, John Norton has been very critical of a lot of literature, and a lot of what he says is right. There's a lot of very confusing things said. But what I don't think I think it is indeed a theorem of statistical mechanics. And I actually had a couple summers ago a back and forth with John, and he tried to poke holes in the proof and was not able to do it. He's not convinced. He still feels like there's something wrong, but at least he wasn't actually able to find a flaw. And the reason I'm talking about it is that I think it goes fairly deep to the foundations of statistical thermodynamics and what it is we're doing, and when we're doing statistical thermodynamics, and there are questions about what we ought to mean by entropy in this context. Right? And so it's also relevant to what we're going to be talking about in the roundtable about the supposed schism between Boltzmannian and Gibbsian approaches. Okay, so starting off. This is a question that I borrow from Shelley Goldstein. I've seen him ask this at various workshops various times. Suppose you've got some thermodynamic system in front of you. Suppose you're not omniscient. You don't know its complete state. And an angel appears. It's an angel because this angel doesn't have to interact with things in order to gain knowledge of it. Angel appears and tells you a much more precise state than you know. Tells you something you didn't know about the thing. Okay, it won't be able to give you its precise state, but a much better approximation to it than you already had. Question: has the system's entropy decreased when you got that knowledge? Now, sociologically, my experience has been everybody thinks the answer is completely obvious. But there are two very different strains of obvious answer. Okay, so one common sort of answer is, of course. One thing that we've learned is there's a deep connection between entropy and information. This is the sort of thing you often get from physicists. And another common answer is, don't be absurd. Entropy is patently an attribute of the physical microstate of the system, and that hasn't changed. And that tends to be the response more common among philosophers. Okay, what's going on here? I'm going to rephrase the question slightly in a way I think that makes the question a bit more perspicuous. Instead of entropy, I'm going to be talking about available energy. And that's a term that has basically fallen out of use, but it was common among the British physicists who were working in thermodynamics, Kelvin and Maxwell. And they tended to be talking about dissipation, loss of available energy, even after Clausius coined the term entropy. They never really picked it up, right? And what do I mean by available energy? Well, suppose you have some physical system you can manipulate in various ways, and some heat bath at temperature T that you can use a heat source and sink. And it starts in some thermodynamic state A, and you're tasked with leaving it in some thermodynamic state B. What's the maximum work that you can extract from the system? And the answer, which we actually already saw in Pascal's talk, is the answer: the maximum work you can get in state searching is a decrease in what Maxwell called available energy, and Helmholtz a few years later called free energy, and it's Helmholtz, what we now call Helmholtz free energy. So it's the different, you ask, like, how much has this decreased, the internal energy minus T times the entropy of the system, and that's the most work you can get out of the system during that state transition. Notice T doesn't have to be the initial temperature of the system. T is the temperature of the heat bath that you have available. Okay, so here's why I'm going to rephrase the question. When you learn the state of the system, the internal energy of the system doesn't change. The temperature of any available heat bath doesn't change. So the entropy decreases if and only if the available energy increases. Got that? There's a negative sign in front of the TS thing, assuming T is positive. So entropy decrease is equivalent to available energy increase. So question: when you acquired, without any interference of the system, physical state of the system, new information about the system, did the available energy increase? Are you now in a position to extract more work from it, given the task of leaving it in a certain thermodynamic state?
What control operations you have?
Exactly. Depends on what you can do with it. If I have some means of manipulating the system, or in David's terminology, control operations, which, given that such that information is valuable to me in extracting work, then yes, the available energy has increased. If not, if you told me something that's no good for me, that's not useful to me, then no, it didn't. And the reason I'm saying that is I don't think either of those common answers I gave on the previous slide were quite on the mark. Because one of them just said, yes, new information means a decrease in entropy. And another one said, well, of course not, no, entropy is a matter of the physical state of the system. If we want to keep a notion of entropy that has this relation to available energy, it has to be a notion of entropy that is relative both to available means of manipulating the system, or control operations, as David would put it, and information about the system. So that's the moral of the story. We want to retain the connection between entropy and available energy as conceived by Maxwell, Kelvin, et al. We have to accept the notion of entropy on which is defined relative to means of manipulating the system and information about the system. And this is actually the moral that was drawn by Maxwell, and when confronted with Maxwell's demon, Clausius responded, Clausius, who gave us the word entropy, responded in a way that suggested he thought, yeah, whether or not you've got a heat transfer depends on, heat is disordered motion that you can't keep track of, you can't control. So whether or not you've got heat transfer depends on means of manipulation. And since entropy is defined in terms of heat transfer, Clausius was pretty much implicitly saying, yeah, entropy is defined relative to means of manipulation. So this, this isn't an eccentric revisionary interpretation of what entropy is. Clausius gave us the word, he gets to say what it means. Okay. Let's talk about process of equilibration. So I have here cup with little bit of coffee. Earlier, it was nice hot coffee. Now it's, disgusting room temperature coffee. And plausibly, if you walked into this room and you found a room temperature cup of coffee sitting there, there is no experiment you could do, not even if we went over to the brilliant experimentalists with fine-grained means of manipulation. They could tell you about the history of that cup of coffee. Was it hot an hour ago? Was it maybe colder than the room temperature an hour ago? Was it maybe room temperature for several hours? If the overall state of the universe is quantum state of the universe is evolving unitarily, there is a sense in which the history of that of this cup of coffee is somehow encoded in the fine-grained structure of the quantum state, but is that just not available to not just to us, but to any beings with anything like us? Right. Okay. And we're familiar with this. The relentless process of equilibration erases records of past distinct macroscopically distinguished states leads to states that aren't distinguishable. So coffee cup being hot an hour ago and coffee cup being ice cold an hour ago are easily distinguishable, but they could both lead to states now that aren't distinguishable. Okay. Equilibration is a dissipative process. Loss of opportunity to do work. If I start out with the temperature difference and lose it, then I could have used that to get some work, and now I can't. And the question addressed by Landauer's principle is every forgetting of this sort dissipative? Landauer was working for IBM at the time. They were engaged in a project of constructing bigger and faster, more powerful computers. And one of the things that Landauer, and then there's a question, are there in principle limitations on the computing power of given physical resources? And one of the things that was a serious limitation on computers in those days was the amount of memory. And so Landauer is saying, well, look, any computer has to have a finite memory. If you keep working and working and working, eventually you're going to have to erase something. And he argued that there's a thermodynamic cost to eraser, and that is what's called Landauer's principle. I don't know about you, but I haven't actually used up the hard drive space in any of the computers I've owned recently. So I probably could have been engaging in reversible computation all this time and not worried about that. But Landauer was really concerned about memory limitations. Okay. And by the way, real computers don't run anywhere close to the Landauer limit, just as real heat engines don't run anywhere close to the Carnot bound on efficiency. Okay, so Landauer's principle, as we'll construe it, is suppose you've got some process and you've got some number of distinguishable thermodynamic states, and you've got some process that takes them all to the same thermodynamic state. Is it possible this process does that without dissipation for every member of the set? So you imagine a process that maybe does it without dissipation for some members of the set, but not everyone. And Landauer's principle says no, that cannot be done, and actually gives you bounds on the amount of dissipation. Okay. And the basic idea is, well, if information about the state of the system is used for extracting work from it, we should be able to quantify the thermodynamic value of gaining information. And if losing information means losing an opportunity of extracting work, you should be able to quantify that. In the literature on Landauer's principle, very often it's just assumed that there is a tight relation between information and thermodynamic entropy, and John Norton and other critics have criticized the literature for that, justly, I think. And so for that reason, I'm going to be very careful not to assume any relation whatsoever between information and thermodynamic entropy. In fact, the proof is going to go through entirely without mention of use of the word entropy. Okay. So I want to talk about what I mean by dissipation and what I mean by reversible processes. This came up earlier in discussion with Yellis. So suppose I've got this system that takes a system that's a thermodynamic state to another thermodynamic state, and this time, for now, I am talking about thermodynamic states, points in equilibrium state space. And of course, the process, it interacts with heat baths at various temperatures. It exchanges heats with those various heat baths, and so I got some process that takes it from a state A to B with those heats exchanged, where I'm going to count heat going into the system S as positive and heat coming out of the system S as negative. And we're going to ask is, well, is there another state process that'll take me from, if I go from A to B, is there another process that takes me from B back to A that closes the circle with this then net Qi over Ti equal to 0. And if that is true, then we will say that the process M is thermodynamically reversible. Yes?
Are you using the same heat bath only in the first?
No. They can be totally fresh heat baths. They can be, they can be different heat baths at different temperatures. Yeah. Doesn't really matter. Okay. And we'll also say it's reversible if there's no upper bound less than 0 on that quantity. Second law of thermodynamics, the one way of expressing it is through what's called the Clausius inequality. If there's a process that takes a system through a cyclic process, so from restores the initial thermodynamic state, exchanging mass heats Qi with baths at temperature Ti, then this quantity, sum over all the heat exchanges Qi over Ti, is bounded from above by 0, less than or equal to 0. And if two states can be connected reversibly, then that entails, going from A to B one way is less than or equals 0, and if I can, reverse it, maybe by a reverse process, changing all the signs. That reverse process also less than or equals 0 means that it has to be 0. And so, if they can't be connected reversibly, the second law entails that this quantity is the same for every reversible process connecting A and B. And that's what allows us to define the thermodynamic entropy. Right. So, if you want to know the entropy difference between two states, just cook up some reversible process that takes A to B and compute that. And the second law tells us it won't, that'll be the entropy difference. And the second law of thermodynamics tells us it doesn't matter which reversible process we used. Right? And the reason I'm saying that is I want to emphasize is that the definition of thermodynamic entropy requires the definition of thermodynamic entropy of two thermodynamic states requires that you can at least imagine or cook up conceptually a reversible process that connects the two states. And sometimes in presentations of thermodynamics, the assumption that any two processes can be connected reversibly is explicit, and sometimes it's implicit. Okay. So what do I mean by a dissociative process? Dissociatory process. Well, it's one that's not reversible. Right? So if I go from a state A to B, and there's no way to go back that closes this and get even arbitrary close to 0, then my process that went from A to B is dissipatory. So a process M that takes me from A to B with these heat exchanges, imagine all the processes that might take B back to A, and if there's a upper bound less than 0 among all those processes, then the process that went from A to B is dissipatory, not reversible. I got the idea? And in fact, this is what we're going to use to measure the amount of dissipation. Yeah. So those who are familiar with the thermodynamic literature will recognize irreversible entropy production, but I promise you, I'm not going to use the word entropy. Okay. Okay. All right. So this is what I mean, by the amount of dissipation associated with a process. Everyone got that? Okay. For example, free expansion of a gas. Standards in the literature, you imagine of a gas that's initially contained by a partition within part of a container. You pull the partition out and let it expand. Okay. No heat in, total energy is conserved. And hey, if I want to go back to this initial state, what do I have to do? Well, I have to compress it. And because the initial and final energies are the same, I'm compressing it, doing work on it. In order to get back to the initial state, I'm going to, since I'm putting energy in by doing work on it, in order to get back to the initial state, I'm going to have to take some energy out. So I connect it to a heat bath and push it in and dump heat into the heat bath. And because I have to expel heat, it's a dissipatory process. There's no way I can complete the process with net Qi over T being equal to 0. To complete this process, it has to be negative. You got the idea? Okay. Okay. Now, this is thermodynamics, and I want to move to statistical mechanics. So something that the Maxwell and others working on thermodynamics in the 19th century, they were also interested in the kinetic theory of heat, and they were developing what we now call statistical mechanics. They realized that the kinetic theory of heat entails that what the second law is originally conceived says is impossible is not impossible, but at best highly improbable. So if I'm doing a Carnot cycle, because of molecular fluctuations, it might happen that on a given run of the cycle, I get more energy out, more work out, that just because of fluctuations in the force on the piston, it might happen that I get more work out than is allowed by the Carnot bound. Of course, I might get less. And what people concluded is, for large macro systems, I will almost certainly not exceed the Carnot bound, and for any system, I won't be able to consistently and reliably exceed the Carnot bound, right? And this means that that's at least strongly suggests that we're going to introduce some notion of probability. And you might justifiably ask, well, in the context of classical statistical mechanics, what does probability, classical mechanics, what does probability even mean? That's a very good question. But the nice thing about theorems involving probability is that they tend to be correct as theorems no matter how you think about the probability. So just choose whatever you want to think about probability and just use that every time you see a probability in anything. And if you think, well, no, probability doesn't belong in physics, then okay, how do you make sense of things like that? Because I think we do need to make sense of statements like that. Right. Okay. Traditional thermodynamics deals with situations and macroscopic results of our operations are predictable. If we want to generalize, we put probability. The standard way to do is put probability distributions over the state space of the system, and then heat and work exchanges are going to be random variables. And what we're going to do is get a probabilistic version of the second law in terms of expectation values of these quantities. And so from here on, I say thermodynamic state, in Pascal had the slide saying statistical mechanical analog of a thermodynamic state, and I think that that's probably better terminology. but in classical context, it's a specification of any exogenous parameters. So, like, in the gas of the position of the piston, etc., plus a probability distribution over the system state space, classical, or a quantum state, possibly mixed. Right? The nice thing about these theorems is that they go through pretty much word for word, whether you're talking about classical probability distributions or quantum states. And the reason for that is we're going to be concerned primarily with probability distributions of quantities that commute. And if you're only dealing with that, then a quantum state acts a lot like a classical probability distribution. Okay. And what I said about getting a probabilistic version of the second law in terms of expectation values was nicely put by Szilard. Consider somebody playing a thermodynamic gamble with the help of cyclic processes and the intention of decreasing the entropy of the heat reservoirs. Nature will deal with him like a well-established casino in which it's possible to make an occasional win, but for which no system exists ensuring the gambler profit. And so he has in mind these no-go theorems for gambling systems. If a casino is in fact not rigged, if the probabilities are as advertised, and on each run of the roulette wheel, you guys might have encountered friends who have surefire systems for winning at a casino. They might think, oh, I'm going to wait until 5 blacks come in a row, and then by the law of averages, it has to average out. So I'm going to bet on red because then red's more probable. And there are theorems if these if each run of the roulette wheel is probabilistically independent, then there's nothing you can do to change the expectation value of your winnings. And if the casino has set the odds correctly with probability 1, if you keep playing your surefire gambling system, then you will go bankrupt. Okay. We're going to have to use the concept of the heat reservoir, the system that's relaxed the thermal equilibrium, and we're going to be exchanging heat but not work with such systems. And the central assumption, I think, that really makes statistical thermodynamics go is that the appropriate probability distributions for heat reservoirs are canonical distributions uncorrelated with other systems. And if I interact with the heat reservoir, then I'm going to become correlated with it. Then what we can imagine is, well, you've got as many different heat reservoirs as you want, and you're going to use a fresh one for each interaction. Or else you say in between interactions, there's going to be some kind of relaxation to equilibrium, and whatever correlations you've set up with that reservoir are going to become irrelevant for future interactions. Doesn't matter. Okay. Not going to be assumed that interactions leave the heat reservoir canonical, only the canonical before the interaction. So if it's not canonical after the interaction, either you let it relax the canonical again, or you just find yourself a fresh heat reservoir to interact with. Okay. Probabilistic version of the second law, and this is a theorem of statistical mechanics, both classical and quantum, is that under those assumptions about how the appropriate probability distributions for heat reservoirs, and no assumptions about the probability distributions of other things, except that they're initially uncorrelated with heat reservoirs, any process that goes from one state, now states are, as we define them on the previous page, they're just any quantum state or any probability distribution over the state space plus a specification of external parameters. This is basically the same as the thermodynamics second law, except we've replaced heat exchanges with expectation values of heat exchanges. And we've replaced a state function with a functional of probability distributions. By the way, when people see expectation values, sometimes they think, okay, you're assuming that the actual value is going to be close to the expectation value. No such assumption is applied. This is completely general. So you might have a situation in which there's the probability distribution. Remember, heat and work exchanges are random variables because we've got probability distributions. Could be have widespread, doesn't matter. This is a theorem. Okay. Okay. And have equality if the process is reversible, if it can be run in opposite directions with expectation values of heat exchange is reversed. Okay. Okay. And so we're going to have a probabilistic version of dissipation. So there's a process that takes a state A to a state B. If there's a process that takes it back, and it is exactly the same as we had before, except now we've put expectation values of heats instead of actual heat exchanges, we'll say it's reversible. It's dissipatory if there's an upper bound on that that's less than 0. And that's how we're going to measure the dissipation of the process. So if I've got a process that goes from the state A to B with these expectation values, consider all the processes that take B back to A. And if there's an upper bound on this quantity than less than 0, then the absolute value of that upper bound is going to be the dissipation associated with this. And got that? I'm just explaining what I'm going to mean by dissipation in the statistical mechanical context. Okay. Okay. Now I'm in a position to state the Landauer bound in terms of dissipation. So I got some process that takes each member of some set of states, distinguishable thermodynamic states, and distinguishable means that there is some measurement I can do that's going to tell me which one. So in the classical, in the classical case, that means that they're probability distributions with disjoint support. In the quantum case, that means that they're density operators with this disjoint support. So for each one, there's going to be, so I've got some process that takes each one of these input states to the same state. For each one, this process is there's going to be a dissipation associated with it. And the Landauer bound says that can't be 0 for each one of these states. And in fact, it gives me a bound. It says this quantity, you take e to the minus delta I over k, k is both on constant, add them up, that has to be less than or equal to 1. And that, if you stare at that for a few minutes, you realize that means that they that means that all of the if there's more than one state, n is more than 1, that means that all the delta i's have to be positive. Because if it's 0 for one of them, then the rest of these terms have to be 0, and they can't. Everyone got the idea? Equivalently, and this, I find this is what you get in Szilard when he's discussing things like that. I think that that's actually the most perspicuous way of talking about it. In the actual literature, you'll find this more common, that if I take some kind of weighted average of the dissipations, that's less than equal to that. And that, of course, looks like a an information theoretic entropy. But these two things are. That's correct. Yes. Right. I just like the upper one better. And a special case of this is when you take every pi equal to 1 over n, and you get that. And sometimes this is what's given as Landauer bound. And this follows from that, but it's strictly weaker. Okay, so if you want to visualize this for 2 states, if I have some processes takes 2 distinguished states of the same state, and have the dissipations delta 1 and delta 2 associated with them, then the The gray shaded area is the allowed part. So there's a trade-off. I can make one as small as I like at the price of making the other one really big. Okay. The consequence. Notice I first gave you a statistical mechanical analog of the second law. This Landauer bound that I guess stated is in fact a consequence of that. And the reason that is we're saying is sometimes in the literature, it sounds like Landauer's principle is being invoked to save the second law from the threat of Maxwell's demon. And that's just incorrect. It's a consequence. It's a consequence of the second law. The second law doesn't need saving. It's a theorem of statistical thermodynamics. And this is, I think, or some of the early literature on thermodynamics of computation and Landauer's principle and Maxwell's demon kind of sounded like Landauer's principle was supposed to be some kind of independent principle invoked to save the second law from kind of threat. But what I guess said it eventually became more or less a consensus. If we're talking about thermodynamics of computation, Charles Bennett is orthodoxy if anybody is. And he says, even though in a sense, Landauer's principle is indeed a straightforward consequence or restatement of the second law, it still has considerable pedagogic and explanatory power. And what he means is if someone gives you a gadget that's supposed to act like a Maxwell's demon and consistently and reliably violate the second law, one thing you should ask yourself, is the entire system, is the demon acting in the cycle, right? And if the demon gets some information about the system and decides what to do on the basis of that, in order for it to make to act in the cycle, it then has to erase that bit of information, and don't forget the dissipation associated with that. That's what he means by it has pedagogic power. That is a good reminder to not forget dissipation associated with erasure of, let's say, memory of the demon or something like that. Okay. I'm not going to go through the proof of the Landauer bound as I gave it. It's in my paper published in the British Journal for Philosophy of Science a couple of years ago. There's also a simplified version on the Philosophy of Science archive. I just want to say that what I just told you is actually a special case of a more general theorem. We can relax the condition of the initial states being distinguishable. Okay. And the way I do that is first I'll define the relative entropy of two distributions as this. Some of you are familiar with this, especially if you work in quantum information theory, things like that. This is one way to talk about the divergence of two distributions is equal to 0 if the same and is positive otherwise. And so for any set of numbers, positive numbers that sum to 1, we can consider a set of mixed states with those weights. And I can consider for each one of these states the relative entropy of that state with that mixture. And if they're all the same, that mixture is just AI, right? Default way. And if any of them are different, then this is going to be not zero, non-zero. And so this is in some sense a measure of the distinguishability of the set of states. So if I have a set of states not necessarily distinguishable, but have some process that takes them all to the same state, can it do it without dissipation for all of them? And the answer is no, except in the degenerate case in which they're all the same. And I can actually get a bound in terms of these quantities here. And so this quantity is 0 if all the states are the same, greater than 0 if they're not all the same. Okay. And that reduces to our previous result in the case of distinguishable states. And I can also consider imperfect erasure. So imagine that I've got some set of input states, and the process takes the input states to maybe some slightly different output states, not exactly the same. And basically, this quantity is a measure of loss of distinguishability. So this is another generalization of a result. Again, it reduces to what I had on the previous slide in the case where all the VIs are the same. All right. Okay. I promised you that I wasn't going to use the word entropy, and the reason I didn't use the word, and I talked about what I was going to talk about called dissipation. I wasn't going to use the word entropy because the critics of Landauer's principle have accused people of unjustifiably equating information theoretic entropy with thermodynamic entropy. I didn't do that. Now, in the proof, a quantity appears is called an entropy. And in the classical case, that's what's known as the Gibbs entropy. In the quantum case, it's the von Neumann entropy. And you would say, okay, these get called entropy. Is there any relation between these quantities and thermodynamic entropy? Well, this is the statistical second law I had a moment ago. This is a theorem. You don't assume any connection of these quantities with a thermodynamic entropy. You just define these quantities and you prove this on the basis of that definition. And if the states can be connected reversibly, this uniquely determines up to an additive constant the functional that satisfies that role. If they can't be connected reversibly, then there will be multiple functionals that satisfy that role. Okay. Now, in the literature on philosophy of quantum mechanics, there are objections to Gibbs or von Neumann entropy having anything. Some people will say it's got nothing to do with thermodynamic entropy. And okay, how does that jibe with what I just said on the previous slide? Because that actually is a theorem. Well, let's go back to the example of free expansion of gas, and let's, for the moment, entertain the fiction that the gas can evolve entirely isolated, somehow or another magically suspend all interactions with the environment. Okay. Okay. Von Neumann or Gibbs entropy is conserved. So, and no heat in or out, so that this is satisfied because left-hand side is 0 and right-hand side is 0. Okay. Okay. But you might say, well, wait. Von Neumann entropy didn't increase. Something wrong because intuitively thermodynamic entropy increased, right? Okay. And thermodynamic entropy is defined in terms of reversible processes. So in order to ask the question, did the thermodynamic entropy increase? We have to ask the question, is this a thermodynamic reversible process? Well, is it? Yeah. What did he say, David? He said depends on your control operations. And that's actually right. So the answer is, if this is a macroscopic gas and we've got anything like feasible control operations, then yes, this is no, this is not a thermodynamically reversible process. If all I've got is a piston, then to get back to the initial state, I'm going to have to expel some heat into the environment.
And you wait sufficient on that.
But I can wait a
You may
sufficient.
have other things.
Right. Yeah, exactly. Okay. So when I say correctly that free expansion of an isolated gas is irreversible, and it is thermodynamically irreversible, on some construal of what that means. Are we saying that quantum mechanics forbids a unitary evolution that takes it back to initial state without expelling heat in the environment? Well, we better not be saying that because it's not true. Okay. And there's various proofs in the literature. The nicest one I know is actually due to Owen Maroney in a paper that sadly he never published, but it's on the archive. If you allow arbitrary Hamiltonian, so imagine you've got some magic genie and you write down any Hamiltonian evolution you want and it can make it happen, then if I have any two quantum states, there is a process that's going to achieve equality, where that is the von Neumann entropy. You looking dubious?
I'm worried that I think I've included something close to that. That strictly speaking, if I want a unitary transformation between low A and low B, they have the same spectrum.
Oh yeah. So I'm permitting introductions of heat bath. Yeah, right. So the evolution of the entire system, heat baths plus system of interest, is going to be unitary, but the system itself isn't necessarily a closed system. Okay, good. Okay. And so differences in von Neumann entropy are indeed statistical mechanical analog of thermodynamic entropies for states that can be connected reversibly. And if I have absolutely unlimited control over the system, then any states can be connected reversibility. So if someone says von Neumann entropy is a statistical mechanical analog of thermodynamic entropy, their eyes are imagining a fictitious situation in which you can do any kind of manipulation whatsoever. You've got this magical genie, or else they're saying something wrong. And both of those exist in the physics literature. Like there are sometimes, there are papers where demonstrably people say something like that, and you go through the argument. You say, okay, they're assuming you can do any Hamiltonian evolution. But it's not always flagged how completely unrealistic that is for certain things. Okay. So in the fictitious case of supernatural powers of manipulations, every evolution is reversible, and differences in S always correspond to differences in thermodynamics. Okay, now if I actually want something usable for humans, I want to have a notion of entropy that introduces limits on manipulation. Right? And so here's the way I like to approach it. So take that system situation where you imagine that a gas evolves isolated into a to fill a container. If it's a macroscopic gas, if I now put the thing in contact with heat bath and let it equilibrate, that's not going to be, those two states aren't going to be macroscopically distinguishable, and they're going to react to any manipulations I have in pretty much the same way. Because I don't have godlike powers of manipulation. So I'll call two states thermodynamic equivalent with respect to some class of available manipulations if the expectation values of working heat exchanges are the same for any feasible manipulation applied to either state, or so close enough that it makes no appreciable difference. Okay. So going back to this example of free expansion, suppose initial state is canonical distribution at some temperature confined to the left half. Let it evolve isolated from that to fill the entire container. Those have the same von Neumann entropy. But let how one be a canonical distribution of support in the entire container. So you take that rho 1, put it in contact with the heat bath. Nothing macroscopically observable changes, but the quantum state goes from a state of very low von Neumann entropy to a state of much higher von Neumann entropy. Okay. And that actually is the difference.
Distribution of the same temperature.
Same temperature, yes. Okay. Luckily, the gases when macroscopic, they're indistinguishable by any operation we can do. And so any operation we can do taking either one as a starting point yields the same expectation values of heat exchanges. Okay. So call this the Leithian postulate. It's as if the system has forgotten its past. It's forgotten that it evolved in an isolated way from the left half of the container. Okay. 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 Statistical second law says for any process that takes, so rho 1 is that low entropy, low von Neumann entropy evolved state. Statistical second law says that for any process that takes me back to the initial state, the heat exchanges have to be less than or equal to 0, which is true, right? We argued a little while ago that I'm actually going to have to expel a substantial amount of heat, and so this is actually going to be negative, but that's less than or equal to 0. But this is true, but not terribly informative, right? Because we don't, by any kind of feasible manipulation, I'm not going to get anywhere close to 0. Okay. But if I'm right, if that for anything I can do, it doesn't matter whether I start with this low von Neumann entropy state or the corresponding canonical state. The second law also tells me that for a process that goes from rho 1 back to tau naught, I can also put that in. And that's also true, and that's a much stronger bound. I got the idea? Okay. So for a typo, that should be coarse-grained with an A. So for any probability distribution, I can consider the class of distributions that are thermodynamically equivalent to rho, and just say, okay, let that be the maximum of von Neumann entropy among all of those. And then it's a theorem that for any, if I want to, go from rho to any other state rho prime, that this is going to be true. Where now I'm putting in the coarse-grained entropy. And so that's, it'll be true if I put in the fine-grained entropy, it'll also be true if I put in the coarse-grained entropy, but because the coarse-grained entropy is bigger, that's a tighter bound if I use the coarse-grained entropy. And obviously, if I've got my choice between two bounds, one of them's tighter, then the more informative one is the tighter bound, right? And the reason I'm emphasizing that is sometimes in the philosophical literature, you get complaints that the move from a fine-grained Gibbs or von Neumann entropy to a coarse-grained one is sort of an arbitrary ad hoc posit, and that's just simply false. This is a theorem. It gives me a tighter bound on what I can do. It's more informative, and so yeah, the more informative bound is there's a point in using the more informative bound if it's available. So it's just simply false that invocation of coarse-grained entropies is an arbitrary ad hoc unmotivated posit. Okay, last thing I want to do is so what I've talked about is a relation between Gibbs or von Neumann entropies and thermodynamic entropies, and some people might be saying, well, wait, why are you talking about these things? Why are you talking about thermodynamic entropy at all? That's an old-fashioned concept. It sort of reeks of steam engines in the 19th century, etc. don't we have a nice, shiny, new, more scientifically respectable concept of entropy, namely Boltzmann entropy? And Planck actually said that in 1909. To have completed the emancipation of the entropy idea from the experimental art of man and the elevation of the second law thereby to a real principle was the scientific life's work of Ludwig Boltzmann. Briefly stated, it consisted of of referring back the idea of entropy to the idea of probability, and what really Planck means probability is phase-space volume. Okay, so can we replace this older idea of thermodynamic entropy with Boltzmann entropy? And just forget about everything I just said, right? Well, I think not. I think each has a role play to the other cannot. Again, if I want some kind of entropy that has this connection to available energy, the thermodynamic entropy is, Boltzmann entropy isn't always going to be suited for that task. And there's an example that you find in the literature, imagine you've got, we're back to the classical situation, but there's a quantum analog too. Imagine you've got some kind of system whose a state space, it can be partitioned into macro states. And instead of having one big macro state that totally dominates the volume, suppose you've got a largest one, but a bunch of smaller ones that add up to the same volume of the large one. Then nothing in Hamiltonian evolution conserves phase-space volume. Nothing in Hamiltonian evolution forbids every state in M1 going to one of these other states. And every one of those other states has a lower Boltzmann entropy. So, as been pointed out several times in the literature, nothing in Hamiltonian dynamics forbids the existence of systems that reliably decrease Boltzmann entropy. Okay. Okay. Does it increase available energy? Well, the problem is, I know that the state is one of these lower Boltzmann entropy macro states, but I don't know which one. And if I knew which one, then yeah, I could exploit that information to do work. But if I don't know which one, then knowing that it's in the union of M2, 3, M3, M4, M5 isn't any more useful than knowing that it's in M1, right? Okay, so it is possible that for each one of these lower Boltzmann entropy states, there's a operation that takes the system back to the original state, extracting heat from water and retaining work. So if I tell you it went to M2, then okay, available energy is increased. It's provable, not possible. There's a single operation that takes every one of them back to the original state, obtaining work in each case. And that's basically Landauer's theorem over again. Okay. All right. So in a case like this, if the system evolves to one of these that's not predictable, which available energy is not increased. So if I want a concept of entropy that has this link to available energy that thermodynamic entropy did, Boltzmann entropy in weird cases like this is not going to fit the bill. Now, for most ordinary macroscopic cases, this is irrelevant, and the Boltzmann entropy difference between two states is going to closely approximate thermodynamic entropy. But things like this do show there is a conceptual difference. So for that reason, I don't think we should just abandon thermodynamic entropy or Gibbs and von Neumann entropies in favor of Boltzmann entropies, because there's a role that those can play that the Boltzmann entropy is not suited for doing. Okay. Has the thermodynamic entropy decreased? So we have this evolution where the Boltzmann entropy surely decreases. Is this a counterexample to the second law as conceived in the 19th century? Should we count this as a decrease in thermodynamic entropy? Well, the interesting thing, if you ask Clausius, well, or if I look at the definition of entropy that Clausius gave, he's implicitly assuming that we're dealing with operations or results that are predictable. You talk about, you do a manipulation, what is the amount of heat you're going to change with heat mass? And so there's a real question of how we extend the concept of entropy to situations like this, which arise in system mechanics, where the results aren't predictable. And remember, in order to get an assured decrease of Boltzmann entropy, it has to be the case that what macro state it ends up is not predictable. Okay. Okay. I think we have a choice how to extend the notion of entropy to cases like this, and it's only a terminological choice. If we want to retain the link between entropy and available energy, we have to say, in absence of information about the final state, there has been no entropy decrease. And what this illustrates is that you can at least imagine cases, even if they're not realistic, in which both there is a decrease, assuredly a decrease in Boltzmann entropy without a decrease in thermodynamic entropy. Okay, and that's it for me.
Thank you. I mean, I agree with pretty much everything, of course. Well, a sort of friendly amendment,
Yes.
really. I mean, I do. You've got basically this sharp dichotomy between, on the one hand, the complete arbitrary manipulations of systems, which obviously is only a thought experiment, and on the other hand, the coarse graining associated with full equilibration and the less principle.
Yeah.
And I do think there's a value in having a sort of broader framework in which those are embedded in special cases, where we just want to say, okay, fine. And any notion of control process I have defines an entropy appropriate to that notion.
Yes.
And so, I mean, particular case would, in your context, I think would be, so spin echo is one nice example in that, if I do have that control, it's used, then I know the system evolved from that state, I can go back. And actually something like the Gibbs the Gibbs paradox case, where I might have a box where the left hand side is one isotope of chlorine, the right hand side is the other isotope of chlorine. If I have the appropriate filter, I'm going to have a different appropriate coarse graining.
Yeah, that's absolutely right. So let's see, where did I have the definition of what I said thermodynamic equivalence?
So you've got a relativization there. Okay, good.
Yeah, right. Yeah, so
good.
I'm absolutely in agreement. There's this notion of thermodynamic equivalence is relative to some class of available manipulations, and hence the coarse-grained entropy will be relative to some class of available manipulations.
Good. Yeah. Okay. Fine.
Yeah. So the intent. Yeah. So it's illustrated with some simple examples, but really it is meant to be exactly the sort of general framework you're talking about.
Excellent. Good. And then just as a quick follow from that, I mean, I think it's also useful to understand a slightly generalized version of the Boltzmann entropy that way. So if my control operations are defined on macro states, and again, I'm sort of saying this advert, I'm pretty sure you know this, then Boltzmann entropy might decrease, but Boltzmann entropy plus the Shannon entropy of the macro distribution is going to be non-decreasing, and it's going to be exactly that quantity.
Exactly right. Yeah. That's absolutely correct and worth saying.
Thank you. I think that part of my question has already been addressed by your discussion, because I was wondering how were you defining these thermal equivalence in the coarse graining? Maybe if you can go to the next slide, I think it is.
Okay, so yes, I have this notion of thermodynamic equivalence, which is explicitly relativized to some class of available.
Yes, with respect to the control that you have over.
And then when I define the coarse grained, I guess, It's
Yeah,
defined in
these
terms
gammas.
of that concept of thermodynamic equivalence, and hence it's also explicitly relativized to a class of available manipulations.
Yeah, so this means that these gammas are all of the states that under this particular set of available manipulations look the same as your state.
Yeah, look the same and behave the same. Yeah.
Okay, thanks. Then my question is for me, coarse grain. When I think about coarse graining, I'm thinking about the resolution that I have to measure my system in a way. But I don't see a clear relation to this concept of coarse graining with yours regarding available manipulations. So is this maybe? But is this maybe related to? I'm trying to think it in statistical terms a little bit. So is this coarse graining going to be defined by the noise around my thermal around my means?
Yeah. So
How should I think about it?
yeah. So suppose I have among my manipulations, I can do a measurement of the state and choose to do something on the basis of the result of that measurement. Then states that are observationally indistinguishable are going to be thermodynamically equivalent. And if the information I gain, so if two states are distinguishable by the measurements I have, and if that information is useful in order to get work, then they won't be thermodynamically equivalent.
Yes, I see. And this sets a bound on how much you can extract out of the system.
Yeah.
Yes. Thanks.
Well, thanks, Wayne. That was beautiful. And I think I agree with everything you say. But now this is I have two comments, I think. The first one is that we've been talking, it was yesterday or yesterday was the first day, right? About how classical thermodynamics or how discussions have been influenced by the idea that thermodynamics deals only with simple systems like ideal gases. Whereas in fact, it's a formalism that's capable of, well, dealing with an enormously wide class of systems, precisely because it doesn't make any assumptions about the microphysical constitution of the system. So it can apply to black holes, it can apply to all kinds of systems that were never dreamt of in the 19th century. One of these types of systems is, of course, the spin systems, like the Ising model, and in which case, as I said in response to Patricia's talk, you have to deal with negative absolute temperatures. Now, I noticed that in your connection with, in trying to avoid the term entropy, you related to the free energy, the Helmholtz free energy, or Maxwell and Kelvin's notion of available energy. And that equivalence.
I did explicitly assume that T was positive. Yeah.
Yeah. So wouldn't it be nice if we could also extend that to absolute temperatures that are not necessarily positive?
Yeah. Let me think about that.
Well, you don't have to answer it. It's just a suggestion.
Yeah, I think that is really, really worth thinking about.
There's nothing in Gibbs or
right,
in
that. I don't know what to say at the moment. Right.
No.
Yeah.
Worry about whether negative temperature systems, the kind of thing. Right?
Yeah, that was my first. Yeah, that's my first inclination. That the T was not necessarily associated with the temperature of the system I'm manipulating, but with the heat as I'm going to use a reservoir. So one thing I could do is basically say, okay, I'm going to add as a stipulation that for something to count as a heat bath, there's no upper bound on its energy spectrum. Um, I don't know if that's what I want to do or not. I have to think about
Yeah,
this.
sure.
Yeah.
Well,
I have to think about how. I think that's a very good question, and it is definitely something that we're thinking about. Yeah.
yeah, to continue that, and I think also that the notion of heat bath is one of the lesser examined concepts in the foundations of thermodynamics, and it's I think the ordinary conception of heat bath really comprises assumptions that are on the border of being contradictory. So it must be some infinite buffer that can take in heat
Right.
without changing its physical state.
Yeah, and I mean, obviously that's not true, but it can be true that something is big enough that
Sure,
that any changes to its state is irrelevant. And actually, there's a way of cheating is you say, okay, I'm just going to imagine you've got this array of heat paths and you're interactive each of them just once.
Yeah. And the other comment I had is that, well, it's one thing to use this term of availability. It's not a question what exactly does it mean. Is it just not, if something is just not available to us because we lack the money to buy it, or is it unavailable to us because of certain measurements limits, or is it due to the laws of physics, or are there other considerations here?
Yeah, I think that's really good because it could mean a lot of different things, right?
Yeah.
Like, I said, imagine you saw some class of available operations, and I think the reason that it's not in the literature, it's not always made explicit that entropy is relative to a class of available manipulations is in the background we have there's a clear distinction between the sorts of things that are feasible and the sorts of things that aren't, and though it is true that if you look at entropy tables, people will sometimes compute entropies for substances that are insensitive to what mixture of isotopes you've got and entropies that are, depending on whether you're going to, care about manipulate things like that. So occasionally it's explicitly relative to a class of manipulations, and I think that there's room for lots of different kinds of distinctions, and there are sorts of things that are technically feasible now that wouldn't have been 20 years ago, right? And there are some kinds of manipulations that, even though they're not forbidden by the laws of physics, we don't think could be feasible for not just us, but any kind of being that like us, that could be an agent operating in the world and not some kind of transcendent being looking at it from the outside. So I think that you're absolutely right, that there's a lot more to be said about different senses in which a certain class of manipulation could be available manipulations. That's absolutely right.
Yeah, actually, I have a question. I was going to
Yeah.
put myself in the queue.
Yeah.
I guess it's kind of related to yours question about availability. I was wondering, I guess when an information connectedly, I guess when, like you said, it's just a math, right? It's just probability, but like, how do you interpret it? And I guess a lot of physicists think about it in a very sometimes radically subjective way. But I'm not sure if you think that's like the right way to think about it, or is that the more objectified version of the information is the right way to think about it? Maybe something like, well, whoever you are, if you are a system of a certain scale with certain physical traits, that you are not going to be able to do certain things on that system, while other things are possible. In that case, it's still information, but it's really just more physics, right? There's no knowledge involved, and that could be a way to sort of respond to like a David Albert type critique.
So I think that's a very good question, and it's one that I intentionally sidestepped in in this, because a couple years ago I wrote a paper which is on the archive called "Probabilities and Statistical Mechanics. What Are They?" Right, or something like that, in which I was wrestling with the question of what should we say about the probabilities that appear in classical statistical mechanics, because what's said in textbooks is either confusing or incoherent, because very often, like in the beginning of the statistical textbooks, they'll say things like, okay, we're dealing with systems consisting of very many degrees of freedom. There's no way we could know the state perfectly, and if someone did hand us the initial state, somehow we wouldn't be able to keep track of its evolution, and that strongly suggests, and so we're going to put a probability distribution, and that strongly suggests that we're dealing with some kind of epistemic notion. Right? It has to do with the degrees of belief. Just for a historical comment, if you look at the discussions of probability in, from the 17th, 18th, 19th century on, there's two different kinds of notions of probability that are there. You have people like a lot of the pioneers of probability theory, like Bernoulli and Laplace. This is the 18th century. We believe in the principle of sufficient reason. Everything happens as a reason. From God's point of view, there's no uncertainty of the relation. Probability can only be epistemic, have to do with what we know about it. But these same people lapse into talking into probabilities as if they're features of physical setups, like as a matter of fact about whether a die is fair, and that's true of Bernoulli and Laplace and everybody. And so in the wake of, and like Laplace, when he's talking about what we now call Bayesian inference, talks about estimating unknown probability. And if probability is just supposed to be my degree of belief, what the heck am I be doing experiments to find out the value of an unknown probability? And Poisson, reflecting on this sort of confusing stuff in Laplace, said like there's two notions of probability. One is epistemic and one is physical, credence and chance. And if you look at what statistical mechanics textbooks say, they share the sort of way of talking that they find in Laplace. Probabilities are introduced as if they're entirely epistemic. Then you have postulates about appropriate probability distributions for equilibrium. So you got the microcanonical for a system that's isolated of known energy. And then they say, well, okay, these postulates sound good, but ultimately the justification for them is going to be tested by experiment. We make predictions on the basis of it and see if it's right. Well, whatever you're doing when you're testing these posits by experiment, you're not doing experiments to find out about your own degrees of belief, right? And so I wrote a paper called "Probabilities in Systems." Actually, I think the title was something like "Subjective, Objective, or a Bit of Both." And I submitted to a journal, I forget which one, and the referee reports convinced me that there's so much ground clearing I needed to do that I couldn't do this as a paper, and I ended up writing a book. And that book, 10 years later, that book was published in 2021 called "Beyond Chance and Credence." So I think that in context of classical probability, I really do think the way to think about this is they have an epistemic aspect and a physical aspect. They're not, and they're what in that book I call epistemic chances. I actually think David has argued that whenever you think about probabilities in the quantum context, you can just import that into classical statistical mechanics. When I look at equilibrate, I'm not convinced that. I still think that there is a role, and I have to write a paper arguing this in more detail. I haven't done that yet. There is a role for epistemic considerations, I think, in even in quantum context, because if you look at, say, quantum equilibration results, if you're going to get finite, not just long run results, but finite time results, there has to be some kind of limitation of control over the initial state. But yeah, so anyway, that's a the nice thing about theorems is that all the probabilities have to do is satisfy the probability calculus, right? And you get these theorems. But I think it is a real question of how to think about probabilities in actual physical application. But I do think everybody has to think, like, if you're going to take statistical mechanics seriously, you do have to think about probabilities. You can't just say we're going to do this all without probabilities.
Next, David.
Yeah, so that was very nice. I I felt that I particularly liked how you started the thing with the angel thing. I think it was very clarifying. So, I'll just say some things because I think actually my question, Eugene just asked it. But I just wanted to say that it is quite common. So I'm from a quantum information background, and it's very common to meet people that just say that entropy is purely subjective thing. And actually, one of the big profs in my research center he's one of these people that are proponents of this sort of view. And I think no, I'm not gonna drop names.
Okay.
So but very, very significant guy, very, very intelligent. But yeah, he adopts view. And then I think one physics student just asked him, then why can we measure it in the lab? You know, why are we supposed to get the same answer if it's completely subjective, right? So and that kept him awake at night apparently. Yeah. So I guess I have a certain question. Maybe it's not very well formed, but I guess my question is something like, is knowledge and control both like necessary and sufficient for decreases in entropy, so called? Like, let's say that, so we have the macro scale and the micro scale, right? And like some meso scale or whatever. And maybe the angel one gives me knowledge, and angel two gives me the control operations, right, on the meso scale. And is that sufficient, necessary and sufficient for some decrease? Or do you think that it's like, oh, I just need the control angel? Because I think we all take it that we need more than the knowledge angel, right? But do we need the knowledge angel and the control angel? What's your thoughts on this? I would think so. Yeah.
So I think the on this notion of entropy, it's relative both to some class of means of manipulation and state of knowledge about the system.
Yeah.
It's if you ask, well, suppose you have a system in front of you and you have some knowledge of its state and you've got a heat bath available.
Yeah.
And ask, well, how much work can you get out of it? The answer is depends on what you can do with it. So if an angel comes, so if I have some certain means of manipulation, and an angel comes along and tells me something that I can use in order to extract work from a system, then yeah, I want to say that that was a decrease of entropy. But if the angel tells me, and similarly, if another angel comes along and hands me some device that allows me to manipulate the system in a way that I couldn't before, such that now I can get more, given what I already know, I can get more work out of it. Then again, there's an entropy decrease. Yeah.
So, but let's say that the angel only gives me the device,
Right.
but I don't know anything new about the microstate, and I don't know which button to press, to extract the work.
Yeah. So if the device now, so I know something about the system,
Yeah.
right? If this device, given what I know, if the device now allows me to extract more work, then yeah.
Okay, I get what you're saying.
Right?
Okay.
But if this device is useless to me, then no.
Okay.
Maxwell, I think, expressed it really nicely. So he's thinking about what can the distinction between heat and work possibly mean in the context of classical statistical mechanics, kinetic theory. And what he says is, to a being that had no limitations on knowledge and no limitations on manipulation, there would be no such a thing as dissipation of energy, because energy would always be available to him. And to a being, no matter how much it knew, a being that had no means of manipulating systems, it also wouldn't need a distinction between dissipated and available energy. It's only to beings like us who are in an intermediate stage where we have partial knowledge of systems and limited means of manipulation that the distinction between available and dissipated energy makes sense. And I would say not just beings like us, arguably anything that could be an agent in the world, like us,
like an entropy for a velociraptor or something.
Was it that mentioned Schrodinger's What is Life? I think it was Patricia yesterday. Yeah. I like that book. And one of the things that Schrodinger asked in this book is, why are atoms so small? Now, on the face of it, that's a nonsensical question because, on what length scale? If I'm measuring atoms in atomic units, then they're of order 1, right? They're not small, right? But a way of sensible question is, why are atoms so small on the scale we're used to dealing with things, or why are we so big compared to the atomic scale? And his answer is that to be a being like us that navigates the world and consumes food and things like that, you have to be operating on a scale where there's some modicum of predictability. And he also argues that all the predictability there is in the world is actually statistical averages of lots and lots of molecular fluctuations. And so, there's sort of an argument that anything that, not just us, but aliens or anything that could be something like us and agents dealing with the world and manipulating it, there would be, some kind of distinction between available and dissipated energy. Yeah.
Just quickly on the comment for this question, I mean, one way to put the hierarchy problem is, why are atoms so large? So depends on your perspective. Yeah, I just want to come back to the point about whether the Landauer principle is something that saves the second law or a consequence of it. Of course, in the way you've set it up, I agree, it's a consequence. But just to pick out one salient way in which you can see what's going on in the idea of it saving the law. I mean, you mentioned the idea that if I have a control process, that I might, in response to an earlier question, I might have a control process, the form of which is if I make a measurement, and then I perform a unitary dependent result of the measurement. Now, if I just allow myself those, and they're as primitive as they just apply unitary in the first place, I can absolutely violate the first law, second law by processes like that.
Yeah.
No question about it. I measure which the system is, and then I apply the right unitary to dump it into some small region. Now, one way to think about that is to say, well, I don't want measurements to be primitive, so I want to say that process must be embeddable in a non-selective structure.
Yes.
But you can also ask, okay, what's the particular thing that needs to be that's going on in that modeling process to restore the second law? And because it's the Landauer effect, it's the fact that the process will store information in these 2 ways. And I think in a context of where there are at least live strategies in quantum information which are prepared to take measurement and manipulation as a bit more primitive and are less committed to the idea they should be embedded in the Church of the Larger Hilbert space, I think there's some value in seeing that a process of that kind is going to have to include a Landauer principle as a primitive principle in order for the second law not to be violated by the rules it allows. Now, those of us who are happy with the Church of the Larger Hilbert space are going to say that's a derived consequence, but it's interesting to see the way in which it turns up as a derived consequence.
Yeah. I agree. And I think one of the interesting big things comes out of all of this is like, standard thermodynamics basically involves, okay, you've got a macroscopic state and you do an operation. They don't consider things like you do a measurement and then what you do is dependent on the state. And one of the things I think that the Maxwell-Demons literature has taught us is if you're including operations like that, where you've got something that a state dependent manipulation, so it's going to do this or that depending on what state it is, that if you don't include the mechanism that's doing that in the system, then you're going to get things that look like violations of the second law. But if you then include that system in your system you're modeling, you don't get violations of the second law. And I think that what happened is some people have derived the wrong lesson to that, is that in every situation you need to look at the total entropy of everything involved. Now, the nice thing about and this is something that I had some back and forth with John Norton with, because in my discussion with Landauer principle, I imagine you've got this time-dependent Hamiltonian. I didn't talk about the systems that are driving that. And obviously there's going to be some dissipation associated with that. And the cool thing is I don't have to, in order to get a viable version of the second law, I don't have to include that dissipation. Like if I've got a system evolving unitarily according to a time-dependent Hamiltonian, I'll get.
Yeah, though to be fair, John might say, I mean, look, there are the standard model has no time-dependent Hamiltonian. So a time-dependent Hamiltonian is ultimately going to have to be physically realized by something with
for the process of analysis, I can externalize that.
Yeah, but I guess my point is there are going to be subtleties what you're allowed. So I mean, I agree with you is what should be allowed, but it's noticeable. You can get this kind of, if you externalize and say, I'll permit myself time-dependent Hamiltonians and not require any analysis of the mechanism.
Yeah.
In fact, it works. Now, John might worry it doesn't work, but I think it works. Yeah. If I allow myself processes of selective measurement and don't require myself to model a measurement process, then it doesn't work. Yeah.
Yeah. I mean, that's right. And the rationale for externalizing certain things and not other things is because basically because that's what you have to do to get a result, right?
Thank you. So I want to elaborate a little bit on the idea that you had about the two different angels. One giving you information about your state, and then the other about the measurements. But I'm just for some context, I'm kind of thinking about the quantum case, because in this case, as we saw in Eugene's case, is very difficult to define a notion of work, and it depends on some conditions. So right now I'm thinking about measurement schemes that not necessarily satisfy fluctuation theorems, for instance. So we will respect the first law and keep positive and convex probability distribution functions for work. So what I'm thinking about is in kind of a situation, like to make it more concrete, where I have two labs, one that is capable of preparing with high accuracy certain quantum state, and one that is, and this lab gives the system to another one that has certain control apparatuses or measurement devices that don't have the same accuracy as the ones that were used to prepare the system. So even though they may have access to the exact information about the preparation of the system, they may not be able to extract as much work as possible because their apparatuses don't allow to do this. Is this like kind of a good conceptualization of the idea?
That's the way to think about it. So, it's relative to you tell me a class of manipulations and we'll give you thermodynamics.
Like they even take the supernorm of the POBM.
Yes.
Exactly. Yeah. Right, yeah, so you like, yeah, so you've got some class of POVMs that you can use, and you can take, the supremum of the entropy with respect to.
Yes,
the
yes,
work that you're
and I think that
Yeah.
there is actually active lines of research, in particular in last week conference by Julia Rubino, where she talks about these coarse graining approaches to this kind of problems, and I think that is it relates very nicely to this conversation. I think.
Yeah, thank you for that.
The angel thing is great.
You like that?
Yeah, very nice.
Great way of looking at it.
Yeah. Thanks, Shelley, for that example, though. I'm putting it to uses that you would probably not approve of. Yeah.